is
So 9/16, right?
yeah, because if I'm gonna take that 3, you're right. If I have to subtract 16/3, everyone, to get C. 3 minus 16/3 equals C, right? I subtract 16/3 from both sides. Then I need a common denominator. Well, that's 9/3. What's 9/3 minus 16/3? Negative 7/3? Is that
Yeah.
right?
Yep.
9/3, subtract 16/3. Again, if you're like, oh, I hate fractions, you could go, let me see this real quick. So I'm getting 9/3 minus 16/3,
Negative 7/3.
negative 7/3. Hey, sometimes students, you did all this work, you got C and they leave the answer like this, but I'll go back to the question, go, what were you asking for? I wanted you to find the original function of x with the initial value. What it means, I can rewrite all this. I can now fill in C. C is what? So here's my answer. My solution to the initial value problem, f of x, the function, is 2/3 x to the 3/2 minus a 7/3. I found C this time. But you can only find C if they give you an initial value, right? They don't give you an initial value plus C, plus C, plus C, plus C. Like minus C.
In definite integral, you don't need the C, right?
That's right.
Okay.
And then eventually we'll get into something called integrals. These things called indefinite integrals, which just deals with. Oh, good. Super job. Hey, what else is weird? Alright. There's one strange one. Only one though. Because that wasn't that bad, right? Somebody agree? Antiderivative, this is all we do, right? F prime of x was n, x to the n. I guess f of x just equals this, huh? Everyone agree?
Mm-hmm.
Works with any alignment well. First, I should put an easy one. What about the special cases? We've been talking about the functions that aren't polynomials or monomials. Some are exponential. Well, I bet you get it.
Same.
What was the derivative of the x? E to the x. What's the antiderivative of the x?
We just x plus c.
Just put plus c. Gotta love e to the x, right? But who's e to the x's inverse? Natural log x. I'm gonna have to put that over here. A lot of you know it's derivative. Alright, what was the derivative of that?
1/x.
Okay. So that means I'll get the y prime equals out of the way. I think I'll down there or up there, huh? Like I've been doing here. Alright, so I know, be careful.
That's x to the power -1, right?
So you're on your test, right?
Uh-huh.
Not that you're like, that's x to the -1 power, right?
Mhm.
And you're like, well, I know the rule. Just add 1 and what? Divide by it. And you'd see it. You're like, okay, here I go. X to the, if you add 1 to a -1, you get 0. And then you'd be like,
Oh,
wait a minute, you can't do that. You can't what? Divide by 0 in math? That's what, undefined?
Mhm.
That's not the solution. So this is that one special case.
So there'd be no.
What is it?
You're not dividing.
You're right, but that, so this would, when this would happen, if you accidentally did it, Amber, you'd be like, wait a minute. This is my special case. I know the antiderivative of 1 over x becomes this what? Natural log of x. So you go, for this one case, for x to a negative 1 or 1 over x, it just becomes a what? Natural log of x. And then I put plus 1.
See,
So just make a note about that. Go, all right, I'm ready for that. The 1 over x, right? 1 over x, 1 over, but everyone be careful. It doesn't happen with 1 over x squared. It doesn't happen with 1 over x cubed. It doesn't happen with 1 over x to the 4th. It only happens with 1 over what? 1 over x. Cool?
So are you just gonna give us the just f of x equals natural log?
That's right.
Or are you just gonna give us the derivative?
Yeah, the derivative, and then you'll find it.
On the test, is it possible we can just do the integral symbol for it?
Yeah, that's what's coming up. I love this. He's got knowledge of calculus. So in 4.9, everyone, and they haven't shown this little symbol yet, this integral symbol which is coming up, it appears in 5.1. Start writing it like that if you're used to it. Now when this is the symbol they write, they go like this. We'll talk more about what this thing means. Right? Now they do put a dx off to the side here. This means with respect to x, this dx here, don't let it bother you. You go, what the heck is that? But we're saying this is equal to the same answer, what was it?
natural log of x.
Natural log of x plus a constant.
Constant.
Put this in your notes for everyone. When you do go backwards on this, the real definition is this. We have to put absolute value bars in this. So why do we have to do that? Because, do you all know about the actual Latin logarithmic function? It's off to the right, so you can't put negative values in it. Like on your calculator, if you took the natural log of -2, it's undefined. If you took the natural log of it, it's undefined. So, if you're going backwards, then you're saying, well, I'm assuming this x was already some unknown variable, then we're going to always have to put what here?
Absolute value.
Does that make sense? I know we didn't do that when we differentiated, but I'm going to put that now. When you go this way, Amber, put this down. That when you do the integral that we're talking about, this antiderivative, we're going to put bars around the x. Because x could have been some negative number originally. And we're like, well, natural log of negative numbers don't exist in the real number system. Absolute value bar every time.
So, professor, so antiderivative of 1 over x is natural log absolute value of x. What about the natural log of x? That's also absolute value of natural log of x. Antiderivative.
That's right.
Okay.
That's it. That's exactly it. Very good. And when you see why we're doing this, give me that. I know kind of three. You go, why am I going to do that every time? You'll probably everyone. Anybody use Wolfram Alpha for support? Sometimes they don't write it there. I noticed that. They'll just put ln, they'll put parentheses, but we really should put that in case someone put into this expression a negative value. Cool? Alright, so I think we've covered every special case, huh? But, see this symbol, everyone? It represents integral. I haven't shown it yet. Some people are familiar with it because they don't introduce this till section what? 5.1? But what we're saying is, if you want to start writing it, you could say, all right, well then the integral of x squared, yeah, you can just ignore this dx for now. We'll talk more about that. It just means you're using the variable x here. See, if they had in calculus 2, you get into like dy's and dt's and stuff. That means you got to integrate it with respect to that letter. Well, if I integrate this with respect to x squared, that means I'm finding the antiderivative of this. I'll put an equal sign. Go ahead, Amber, pump it up by 1, x to the what? Third, divide the
3.
3, and then I put a plus 1.
So whatever your, okay, yeah,
So if you want to get used to that symbol, if you want to start using it, Belraj was like, I'm going to write it like this in my notes because I'm going to get used to that. This is how you can write antiderivatives. It's called an integral. Now there's some meaning to this because it has some application. It deals with area under curves and stuff like that. That's what I want to build. I want to make sure you understand that. So it's an elongated S though. Doesn't it look like an elongated S? Like an elongated S, like you're summing something. Something's getting infinitely summed. There's a summation of an infinite amount of values and stuff. Infinite amount of like rectangles, if you will, and you'll see it when we build on that today. But if you just wanted to start writing that now, all right, since you mentioned it, I was like, yeah, let's show it to the class. It's like a stretched out elongated S, right? What's on the cover? Anyone see it? There it is. Kaboom. I know. There it is. The integral symbol, it's like an elongate antiderivative. Antiderivative. Now eventually we'll put some numbers on here today. And that'll mean something. You get to plug them in. Cool. I think we've covered all the what? The crazy ones, but and when this happens 100 times in Calc 1 and Calc 2, be careful. No, 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 no. People do it all the time. That's not right. Hey, can I erase this?
Mhm.
We got it. Pump it up by 1, divide by that number.
So
That's
you
not
use
it.
X to
That ln of x, that natural log of x is only for a what? 1 over a simple what?
X.
X, that's it. So this, you're back to that rule. So let me get this out of the way. You're back applying that rule. So think about this. This is like us saying this. I'll write it again like this. You're like, all right, there's some derivative of x. It's 1 over x squared. Who can write that so it's up in the numerator?
Negative
X
2.
to a negative 2.
You got it. Everyone agree? X to a negative 2?
Mhm.
Alright, now, be careful. You gotta pump that up by 1 integer and then divide by that new number.
So
What's negative 2 add 1?
Negative 1.
Yeah, you're like negative 2 on a number line, add 1, you're like, you didn't go to negative 3. Negative 2 plus 1 gives you a
negative 1.
negative 1. So I'm gonna write this. X to a negative 1. Now you gotta divide by this number, which is a,
Negative.
and then I have to put plus what?
C.
C.
Can you do negative 1 over X?
That looks way better than that. Please do it. Cal, please write it like that. Don't leave it like that. Let's never leave negative exponents. It's like, rewrite this. That means 1 over x, right?
Mhm.
And it's negative. So she's saying just write negative and then put the x down here. You could put that minus like right in the middle. See that negative that appeared? Just put it off to the side. You got a 1 over x and then plus. That's way better because eventually they're going to be like this. Amber, plug in x equals 3. And you're like, okay, you're 3. Looks weird when you plug it like that. You know? So here, let me write it like this. Then this means, now I do that on my test, and I want to check. I want to check my answer.
Take the derivative.
Take the derivatives. You should come back to that. You can check all these. Every one of them. But some will get into, you go, when does that chain rule popping up? I'll tell you, not until section 5.5. We're in 4.9, right? So we'll spend the bulk of the time on that. It's way down at the end. 5.5 is called the substitution rule, and it's the reverse of the chain rule. It's fun though, you'll like it. You go, what do I do? And you'll do it every time. Cool. Alright, so we'll do some more in 4.9. I'm looking for a weird one. So I'm scanning page 349. If anybody's got page 349 open, feel free to scan for a goofy one. I will too. If I tell you it's not worth it, we're not going to deal with it now, that's okay. Okay, I think the strangest one I saw is number 34. This is the weirdest one I saw. 44. If you see one, let me know. I'll tell you like, oh, that's good or that stinks.
41 also.
Or 42.
I saw this one. First of all, they used T. And they had that. Now what do they want you to get? F of T. Now, they wrote this off to the side, everyone. So what kind of problem is this? Initial value.
Theorem.
Well, I like that theorem. No, it was an initial value problem, but
Oh, yeah.
hey, how about this, Amber? The initial value theorem is if they give you an initial value you got to plug it in and figure out C, right? I also, when I want to do, before we jump to the next section, let's definitely do ones like 59 and 61 and 63. They got the trig functions. We haven't done any of those yet, right? They're easy though, just SES, go that way. But I should put something else down. Charlie Sheen, Charlie Sheen, Charlie Sheen, Charlie Sheen, this is pi over 2, right? That's pi. That's 3 pi over 2.
Mhm.
This is the point 0, 1. This is the point,
Negative 1, 0.
this is the point
Zero.
1, 0, and then note down here a 0 and a what?
Negative 1.
Because when we get a plug, if we're gonna have to do initial value problems, everyone, they always like to do things at 0. They want to make it easy for you to figure out values. So get used to that. We're thinking about you're gonna find the sine of 0 and the cosine of 0 and the sine of 0 and the cosine of 0. You're gonna get used to like just knowing these, so you don't have to keep going back to the calculator to figure out what the heck's cosine of 0. You get tired of it. You just go, I know cosine of 0 is 1, sine of 0 is 0. All right. I'm gonna continue to write this way. Remember, just for emphasis, antiderivative. All right, what's t become?
T squared over two.
Good job. Sometimes I see that on a test. What's the error? Right. Now it depends. What if a student did every problem perfectly right and they did this once? Oh, LOL, right? You're like, they meant this is what, it's just something I do. Something I might do on the board. But if a student did on every problem, you're like, then you're concerned. Does that make sense? It sometimes will happen. You'll go, oh, for crying out loud. You'll laugh. You'll go, I did derivative. I meant to do what? Antiderivative. So this becomes t squared over
2.
2. Now here's that t to the negative 3. What's negative 3 add 1?
Negative two.
And then plus but look, I have to, look at this. What does this mean? I gotta find the what? Let's find C. Now, what's another way to write this?
So f of 1 equals to 1 square over 2
Minus
minus.
1 in top,
Mhm.
2 stays down here.
T squared. T squared.
Don't I go that? All right. And where's this going?
T.
That's gonna be t.